Welcome to Space News from the Electric Universe, brought to you by the Thunderbolts Project at thunderbolts.info. A new scientific study has further deepened one of the long-standing mysteries of solar physics. For decades, scientists have struggled to explain why the solar wind accelerates as it moves away from the sun, in defiance of gravity. In more recent years, theorists have suggested that so-called transverse magnetohydrodynamic waves could explain both the problems of solar wind acceleration and anomalous coronal heating. However, for the first time, scientists using the Solar Dynamics Observatory have directly measured the, quote, transverse wave motions in solar polar plumes. They have found that the energies of the so-called magnetic waves falls 4 to 10 times below the minimum theoretical requirement to explain the acceleration of the solar wind. The authors of the paper state, transverse waves cannot be the dominant energy source of the fast solar wind in the open field corona, and so we must now consider the contributions of alternative energy sources in coronal holes. Proponents of the electric universe have long argued that magnetic phenomena that exclude the contribution of electric currents will never explain the mysteries of the sun. Let us explore why this discovery is so significant for the electric sun model.
The paper concludes that even in a best-case approximation, the transverse magnetohydrodynamic waves can only supply about 1/10 the energy needed to explain the solar wind acceleration. And this is a huge result. Up until now, there have been no observational evidence to determine how important this form of plasma oscillation would be. Now, there have been plenty of theoretical papers and papers based upon computer models where the investigator is free to manipulate the computer program to give the results needed. And I know all about this. I did exactly the same thing in my own research as a graduate student. You can tweak the computer algorithm to give you your expected results. So what's so important about this paper is that they are looking at the sun and they're taking measurements from the sun. And their results are, no, this form of plasma oscillation does not account for the solar wind acceleration. And this reminds me of recent observations of the convection on the sun. There were plenty of published computer models about how much convection there must be happening under the surface of the sun in order to account for the heat transport. In the fusion model of the sun, we assume there's a nuclear bomb going off in the center of the sun, and then we must calculate how heat is transported from the center of the sun out to the surface. And many papers were written about this with headlines like "Mystery of Solar Convection Finally Solved," but they were all just computer models. And then, recently, someone figured out how to actually measure the convection going on just under the visible surface of the sun, and the observed convection was about 1/100th of what is needed. So the observation of the real sun did not correspond at all to theoretical models. So bringing this back to the paper that we're talking about now, the authors conclude from measurements of the sun that all this talk about transverse oscillations causing the solar wind acceleration is just not right. And they've basically showed that all the magnetohydrodynamics and a fusion sun assumptions are not giving us the right answers.
The man known as the father of plasma cosmology, Nobel Prize winner Hannes Alfvén, famously warned astronomers and astrophysicists that the failure to include electric fields in their solutions for space plasmas would inevitably lead the space sciences into a state of crisis. Many decades later, why has mainstream science still yet to heed Alfvén's warning?
It's almost ironic that Alfvén's name is associated with the magnetohydrodynamic solutions. A bit of history would be good here. Hans Alfvén, as a young man, studied plasmas, and he proposed a radical simplification by saying that there are no electric fields in plasmas. Now, why did he say this? Well, he said this because if you make that radical assumption, then you can write really simple equations, and you can solve those equations to predict results. When you include electric fields, the equations are just too difficult to solve. So these simplified equations are the magnetohydrodynamic equations, the MHD equations that you see written about so often. And they're the same equations that almost all theorists continue to use today. So what is ironic is that not long after Alfvén proposed these models, he himself renounced them as no longer being useful to study plasma systems, because the simplification was so extreme that it did not actually describe real plasmas. And Alfvén basically said, stop using the MHD equations that I made up when I was a young man. They do not describe real plasmas, since real plasmas have electric fields. So coming back to the question, you have to consider the social dimension here. Any young student, young physicist, they need to publish, they have to have results. So you can either go the difficult route of actually measuring real life messy plasmas, or you can take a simplification like the MHD equations and you can write your thesis and publish your papers. And I've been there and I've wrestled with exactly that question. And I have taken the simplified version many times to write my papers. So it's not blaming anybody. I know the problem, but we have to understand that these magnetic solutions that everyone keeps talking about, they just don't apply to real life.
The acceleration of the solar wind as it moves away from the sun remains a seemingly intractable problem for solar physicists. Why does the mystery remain unsolved in 21st century science?
Well, it's such a mystery because something is missing from the explanations. And I, as a scientist, do not yet know for sure if including electric fields around the sun will answer all the open questions. But I do know that if you remove electric fields from the possible solutions, then you are left with only the physics of expanding gases, kinetic theories, and the magnetohydrodynamic equations we were just talking about. I do find it fascinating that many of these models, the kinetic models, for example, of expanding gas, actually come very close to describing the solar wind acceleration that we see. But the fits are not close enough, and everyone admits that the kinetic models, for example, do not work on their own. Now, there's another aspect to all this, which is the connection between coronal temperature and solar wind speed. And you'll sometimes see these discussed separately, sometimes together. As a physicist, these are two different things. The temperature of the air is one thing, and the speed of the wind of the air is a different thing. So on a cold day, the air feels cold because on average the air molecules have a low random speed. It's about 1,000 miles per hour. Now we sense these average random movements as temperature. But the wind is different. We feel the wind on our face, and wind comes about because there's an average movement in one direction of the air molecules. And on Earth, wind speeds are like 10, 20, 50 miles an hour, which is very small compared to the thermal speeds of 1,000 miles per hour. So when we look at the sun, we bring these two earthly ideas to the world of solar dynamics, and we look for the speed of the solar wind, and we look for the temperature of that solar corona. And the difficult part is, in an electrical model, these two may not be separable in the way that we are accustomed to on Earth. So we may have to be changing how we talk about temperature and speed of plasmas around the sun. There are various ways that electricity might play a part in the solar wind and the heating of the corona. For example, there are very clear measurements from satellites that streaming out from the sun, there is a constant progression of what are called traveling electrical double layers. Now, these double layers are a plasma phenomena where positive charges build up on one end, negative charges build up on the other end, and they represent a small drop in electrical potential. And these are kind of like water waves that you would see on a stream that was flowing downhill, down a mountain. You would see little jumps in the water as the water flows downhill. Well, it's the same electrically streaming past us from the sun. And if you take these little waves, these little electrical drops in potential, and you add up all of these heading back towards the sun, you get a total of about 600 volt difference between the Earth and the sun. Now, of course, this is really an approximation because we're just measuring here on Earth, but 600 volts is a pretty modest electrical difference. And that electrical double layer, as I said before, is polar. It has positive charge on one side, negative charge on the other side. If you put this into an electric field, that little dipole will accelerate. So with the model of an electric sun, causing little dipoles to accelerate, the model works pretty well. Now, does it work to fit all the data? We don't know yet. We have a lot more investigation to do on this question.
For continuous updates on space news from the electric universe, stay tuned to thunderbolts.info.